Hi, y'all. This is your recording for Monday, August 24th, review section on inequalities and absolute values. Please notice in the red letters up top that you have a quiz coming up on Wednesday. If you need help, schedule or come into time for tutoring or send me an email or comment in the Google Classroom. Pause the video right now and try these 3 problems as a warm-up, please. All right, I hope you got false for number 1. This is saying that the real numbers are a subset of the irrational numbers. And this is false. I'd accept a lot of different reasons, but you might say because rationals are real numbers, but rationals aren't irrational. Did you notice I used the wrong symbol? I used the element symbol. It's Sunday evening. I have to get back in the hang of it. I relaxed this weekend. Okay, so rational numbers are an example of a real number that's not also irrational. So, and if that was just a whole bunch of words to you and you were like, I don't know what she just said, remember, here's a visual. We had that family, that number family tree that we talked about last week that kind of went like this. We had the natural numbers and then the whole numbers and then the rationals. And then the, goodness gracious, I really told y'all it's Sunday evening, I'm not getting this right. After the whole numbers comes the integers. And after that comes the rationals. And if something's not rational, then it's irrational. And the combination, or the rationals combined with irrationals, was the reals. And we said that anything going from the bottom up is contained in anything above it. So naturals are contained inside the whole numbers. But anything going from the top bottom is not contained. So if we're going back and looking at the original problem, the real compared to the irrational numbers, that's real, there's irrational, so we would say real numbers are not a subset of the irrationals. The irrationals are contained entirely in the real numbers, but that's not true and vice versa, the other direction. For number 2, we have this set of 3 elements, and we want to know if that set is a subset of the rationals. That means do each one of them pass the fraction test? 2/3 absolutely does. 1 1/4 is a mixed number. It absolutely does. 3 is a whole number, an integer, and you might think, well, it doesn't look like a fraction, but remember, it can be written over 1, so it does pass the fraction test. So this is true. If even one of those elements failed, the whole set fails. And then 3 is false. 6 is not an element of the naturals, where the naturals are 1, 2, 3, and so on. But when it's false, you have to give a reason why. This could sound different ways. I would go with false because 6 is a positive whole number. And we know those are natural numbers. Or 6 is a counting number. That was another name we had for the natural numbers. Something like that, as long as it makes sense. This was the point of the lesson where I was going to take questions on last week's homework, but you are doing this asynchronously, so we cannot do that. And then this is today's lesson. We're actually reviewing 2 separate things today, but they weren't both long enough to make their own lesson. So we're going to talk about inequalities first, and then we're going to switch our brains over to talking about absolute value. So I'm actually going to skip a few slides ahead for just a second to show you what our goal is on this section. Our goal is to read short sentences like this and rewrite it as a numerical expression that uses inequalities. Remember, with symbols like this, less than, greater than. The thing is that I have found students, they often forget how to read it or which direction it's supposed to go. So or what kind of words would indicate which one you're going to use. Like if the problem just straight up said something is less than or something is greater than, it'd be easier to know what the symbol was. But different phrases mean different things, and it can be tricky. So what we'll do before we get to these examples is we'll review the symbols and some of the terminology that go with them. When you see these two that look like they're pointing to the left, when you come across that, you would read it as less than, or less than or equal to. So if it's looks kind of like an L, this looks kind of like an L, but it's shifted, then you think of the fact that the word less starts with L, as does the word left. So, and it's pointing to the left, so you'd say it's less than. So if I had this written, right, in symbols, we've been talking a lot about notation. So this is notation for the idea that 4 is less than 5, right? It's also true that 4 is less than or equal to 5, which was this next symbol right here. So if it looks kind of like an L, that's what you would read as less than. The next pair of symbols, greater than and greater than or equal to, you know, if I were to just flip that form 5, like if I flipped this entire thing around the other direction, so I just have to flip it like 180 degrees. But anyway, notice that I flipped the places of the 5 and 4, but I also took that symbol and it's also pointing the other direction. It's still a true statement. 5 is greater than or equal to 4, even though the symbol is flipped. So the bigger thing, what we're about to we'll talk about in a minute, is you remember the alligator mouth. The alligator mouth is always open towards the bigger quantity because it's hungry and it wants to eat. And it's pointing towards the smaller one because it doesn't want that one. So it's pointing at it like, haha, I'm making fun of you. I don't want you. You're measly little 4 and you're not going to fill me up. I want the 5. It's going to make me full. And if that didn't make any sense to you, just strike it from the record. So it's, like I said before, it's easy when the sentence straight up says less than or equal to, or greater than or equal to, but it's not always that clear. So here are some phrases and words when you do your exercises on your homework or quiz or test that would be helpful. If you see these words, you would use those symbols. So under or below, you would use the less than sign, right? Kind of looks like an L that's been rotated. If it says no more than or a maximum of or at most, you would use less than or equal to, because it could actually be equal to the upper quantity that it's talking about. Like if I said, I can have no more than 35 students in my classroom, which is, you know, that's how many desks I have, then the number of students in my class has to be less than or equal to 35. So if I didn't know how many it was, like it's just some number, the number of students has to be less than or equal to 35, right? 35 is the upper limit, so the alligator mouth is opening to it and pointing to the smaller thing, but it could also be equal to. And then if your phrase was above, more than, or over, you know, it would be greater than. Something would be greater than that amount. And so those are the symbols that you would use when you see those phrases. So here we have the basic steps for writing an inequality, which is our goal for this part of the lesson. To write an inequality model for a given statement, you first select a variable to represent your quantity of interest. So I kind of did that in that last example when I said the number of students in my room has to be less than or equal to 35 because that's how many desks I have. But we don't, but that number sign or pound sign, or in 2020 we call it hashtag, that's not a variable that we generally use. We usually use like X, right? We usually would say X. And we would say let X represent number of students. So that's usually how we do that. And then step 2, so that's me selecting a variable to represent my quantity of interest. And then step 2, use the appropriate inequality symbol and amount given to write your model. This is a model. X is less than or equal to 5. It's a mathematical model. And so we're going to do that for a couple of examples. Again, just as a visual reminder, the inequality symbol. So a lot of times, so people will hear me explain everything I just explained and like, oh yeah, I totally get that. And then when it comes time to writing their own, they get confused again. So if you can always just remember, the inequality symbol is opening to the bigger one and pointing to the smaller value. So it's like a hungry crocodile or alligator or whatever this green thing is with teeth. It's opening up to eat the bigger cupcake, and it's rejecting, the smaller one. It's got its back turned to it. It doesn't want that. Same, so that's less than, right? Because it looks kind of like an L. Let me write an S. Less. And then for this bottom one, that's greater than, okay? It's opening up to the bigger pizza and it's pointing to the smaller one. It doesn't want the smaller one. It's rejecting it. It is biased against the small pizza. So if you can't remember which way to point, always points to the smaller one, opens to the bigger one. If the symbol looks like an L that's kind of rotated, that means you read it as less than. So pause the video and take a second and try these on your own. So hopefully, if you weren't sure which way to point your inequality, you went back to the section with the examples of different phrases you might see. And you'll see in that list from a few slides ago that more than is definitely on that list. So that list said if you come across the words more than, you're going to use the greater than symbol somehow. And then your steps from the last slide said step 1 was to identify a variable. So step 1, we will let X equal the quantity of interest, which is how much Antonio must spend to get a discount. Okay, so we'll let X equal the amount of money he must spend. And then step 2 is writing our inequality. So we already know it's going to be a greater than thing, but how do you decide which one is X going on the left or 100 on the right? Well, X has to be more than 100. So X has to be bigger than 100. So the alligator mouth is opening up towards the X. So X is greater than 100, right? Pretty basic example, but it's a good way to just review all the little details about how to write these. It's been a long, not only has it been a long summer that your mind could have forgotten, it's been a long spring break. You haven't been in proper school since before then, so so pause and try this example if you haven't already. So this says Julia must be at least 60 inches tall to ride the roller coaster. So step one, I'm going to choose a variable to represent my quantity of interest. Let's use capital J this time for Julia. We'll let this be her. So what is it, the thing that we're interested in? We're interested in her height. This is Julia's height. And then the second thing we want to do is write our inequality. And this time, just to mix things up, I'm going to just write down the number on the left, okay? Well, if I do that, it messes up from the slide. Oh, okay, never mind. We'll just go with the, see, I was going to be different, but then I would mess up this slide right here. Well, actually, let me see. Actually, our phrase of at least isn't on here, is it? So, oh, yes, it is. I didn't talk about it. Dang it. Dang it all the heck again. So if you have no less, let me do it different color. Ah, dang it. I'm not sure Sunday evenings are the best time for me to do a video. I think I'm not in the mindset. Keep messing up. All right. So our problem that says at least, and so we're going to use this greater than or equal to symbol. What I was going to do was walk through the steps of how you could do either direction and still get it right, but I don't want to be too confusing, any more than I already have been. All right. So the height of Julia is J, must be at least, which our notes said should be greater than or equal to 60 inches. All right, and the reason why it has the equal bar, because when you use that phrase at least, it could actually also equal 60. So that concludes the inequality portion of our lesson. So let's take a little brain break. In class, we're going to take a brain break, but you're at home, so you can just enjoy this meme that I gave the class. The poor donut. So worried. Couldn't find the center to calm down if you wanted to, because it does not have one. All right, so that was the little brain break. Let's talk about something completely different. And it's called absolute value. So here is the definition of absolute value. It's the distance a number is from 0 on the number line. And distance, I want you to remember, is a physical measurement. And so if absolute value is a distance, we know that it cannot be negative. Right? When you measure distance, it's in the physical world, it's always positive. We have, just like everything we've been learning so far this year, there's a notation involved here, meaning the symbol that you use to represent something. And it's these two bars around this X. So any number you see, once you put the two straight up bars around it, you're now asking, how far is that number from 0? So if I had bars around 5 and I said, how far is 5 from 0? The answer would just be 5. So once I perform the absolute value, the bars go away and your answer is just 5. And it'd be the same if I had the bars or absolute value around -5. The question remains, how far is -5 from 0? The actual distance, if you counted the spaces and you measured, it's 5 places from 0. +5, because distance is always positive. And so one place you can use absolute value is in physics, for example. Sometimes when you've got something going in an opposite direction, we'll measure it with a negative number, but the actual distance that it's gone is a positive measure. And we're going to practice with that just a little bit. And then we have, this paragraph right here is a second idea that we're going to talk about today. I don't want to say it out loud right now because we're not there yet. But I do want to talk about this thing right here. right now. The absolute value makes negative numbers positive. That's like a shortcut to this whole section. Real quick, back to the -5 and the +5 absolute value, just to show you again the distance of a number from 0. So here's 0 right here. When I'm asking for the absolute value, I mean literally how many units away, if you were to count it, is 5 from 0. You have a measuring tape or something, and it's 1, 2, 3, 4, 5 away. So the bars go away. The reason why the bars go away is it's indicating that we have already answered the absolute value question. So the bars are gone. Similarly, if I wanted the absolute value of -5, how far is that from 0? Well, you count the spaces. 1, 2, 3, 4, 5 places away from 0. The bars are gone, and your answer is 5 places. Okay, you haven't actually done any math to the 5 or the -5. You've just performed an idea, a concept, or a function. You've answered the distance question. So you take a moment, pause your video, and try these. Now this slide gets to that one spot that I skipped over here in green. Let's look at that now. You should always combine all values inside the absolute value before evaluating it. There's a lot of value in there. Evaluate, value. What this means is you kind of treat your absolute value symbols kind of like parentheses in the order of operations. You do any math inside there first. In fact, some people don't even teach P for PEMDAS. They teach G, where G stands for grouping symbols. Anything that groups operations together. So that could be parentheses, which we usually think of for PEMDAS because P, but it could also be absolute value bars. It could also be radical symbols or roots. So for our case today, it's absolute value. So think of it kind of like parentheses. You do the math in there first. So -3 + 4 is 1, but I haven't done the absolute value yet. Now I take the absolute value of 1, and it's 1. Let me show you the wrong way. This is wrong. This is bad math. But I want you to see it so you don't do it. Bad math would be this. Pause the video and think about what my bad math was. But it seems almost like it makes sense, but it's not. It's bad math. So the bad math was someone comes along, they see the two numbers in there, they see the absolute value. They take the absolute value of the -3 and get 3. And then the absolute value of the 4 and get 4, and they add it to get 7. But that's incorrect, okay? So you don't want to do that. All right. You pause and try the second example, please. All right, so for the second example, this negative is out front. This is the very last thing we're going to do. It's almost like well, it is kind of like a -1 times whatever you get after you do the absolute value. But before you can even do the absolute value, you have to do the math inside of it. So this is really what I have next. I have bringing down this negative because I'm not fiddling with that yet. Not doing the absolute value yet. I'm just doing the math inside. So that's 2 minus 5 is -3. Then now I can do the absolute value, the -3 part, leaving that other negative out front because I'm not fiddling with that even still. Just doing the stuff I highlighted in purple. The absolute value of -3 is +3. Now we attach the negative from the front. And this is what we get. So your grade for the day, don't forget to do your attendance, and your grade is to do the homework, self-check it. The directions will be in your Google Classroom assignment, and this will be due by 11:59 on Tuesday. Last week I made it 11:59 the same day, but now I wish I hadn't done that. So I'll give you the extra day. And quiz on Wednesday, don't forget.